Hi all, welcome to GradStats 2024 Lab Series. In Lab 7, we're working with t-tests, and when we're using a t-test, it's when we want to compare the averages on a continuous outcome between two things. What two things? It could be two groups, two different occurrences or time points, or matched pairs. It could be between a sample and a population. For our Lab 7, we're going to run an independent t-test and a paired samples t-test. And the results of a t-test tell us if the difference between those two things is a significant difference or not. So materials you'll need are linked in the description and include the two data sets we'll be using and your Lab 7 script that you'll work with. And you might want to grab the lab sheet that we use with SPSS just to look at the write-ups. So grab those things and we will get started. Okay, now that we have our RStudio up and running, we're ready to walk through our Lab 7 script. We're going to conduct an independent t-test and a paired t-test. And again, it's because we're comparing between two. In the independent test, we're comparing between two groups, and in the paired t-test, we're comparing between two time points, measuring the same person twice. So to get ready, we need to have some packages installed, and I'm going to go ahead and load up Tidyverse and Haven. Haven is used when we want to import a SPSS dataset. Part 1, independent t-test. Is there a significant difference in the average self-esteem scores between men and women? So two independent groups. Let's go ahead and import our dataset, and we're going to work similar to our data handling in Lab 2, which was descriptives and visuals. So you might want to have your Lab 2 work available, because you can copy paste a lot of information from that and make the adjustments so that you have this to work with. So you need to have survey.sav in your working environment right there, and you already loaded Haven. So what we're going to do is just read in that survey.sav into an item that we're going to call Lab 7 in the environment. And we should have 439 observations of 130 variables. And again, I'm just pulling over code that I used in Lab 2 to help manage and prep this data. For example, in Lab 2, we brought in a data set and we did all of these setting up factors, right? So we have it all ready to go. Just copy paste over to your Lab 7 and then make sure you change all the Lab 2s to Lab 7s. Easy to do because you can do a Control F, which gives you this little add-on area in the top, and do a find replace. All the Lab 2s, turn them to Lab 7, and then that would replace all of those. So I'm not going to do it now because I already did it before. We need to change the ID variable to a character, and then adding these new variables, because I'm going to turn them into factors and then have them as a new variable instead of overwriting the old one. So I'm going to be adding more variables to the data set here for gender, for marital, child, education, source, and smoke. So now I'm up to 136 variables in the data set. And then just like before, we're going to select just some of those variables so we're not working with 136 of them. We don't need quite that many. So Command Enter. Now I have 439 observations of 18 variables. Way more manageable, easier to see as a table in in our script area here. So, good. Now, preliminary, that's the stuff you're doing ahead. Sometimes you're gathering descriptives to help you give a good narrative to your reader about what this data set is about, but you definitely want to grab descriptives on your variables that are going to be in the model. And with our research question being what what are the differences in total self-esteem by gender, we want at least those two variables described. But we can get more and be able to have some kind of conversation introducing the data set to the reader. So I'll load up janitor because it seemed to have a really good table for summarizing these frequencies of the categorical variables. And we'll take a look at sex, marital, child, and education. And this is stuff we did in Lab 2. So we have how many in each level, the percent of the whole, and we typically use valid percent if we have some missing values, unless our question is relevant to the missing cases. So, cool. So we need descriptives for that continuous outcome of interest, total self-esteem. So what I have here is telling R, use the data set or the thing in the environment called Lab 7.1, then summarize the following information. Summarize the mean of total self-esteem, ignoring the missing values, and call it mean underscore TSLFEST. And also give me the standard deviation of total self-esteem, ignoring the missing values, and give it the name SD TSLFEST. So it gives it to me down there, and I have my mean and standard deviation of the whole total self-esteem variable, which is something I'll need to report. And I can give it a name, just take that whole stuff and copy, paste, and give it a name so that it'll stay in your environment when you want to go see it later. So now I can click on that so I can view and have even longer numbers than what they gave me in the console. Like if I needed to go to 2 or more decimal places, the table has it, whereas the console only went out that far. So, okay. So if we add a few extra directions here, we can also get R to tell us the mean and standard deviation of total self-esteem specific to each gender level of the categorical variable. So I have the same information that I had before, but I have this line in the middle. This is saying group by the sex variable, then summarize that stuff. And I'm giving it a new name in the environment so I don't lose the one for the overall total self-esteem. So it's the same thing with this little add-in saying to group it by male and female. So let's take a look at that. So lots of information that I can use to report about total self-esteem by gender type in my narrative, especially as I'm describing the constructs of interest, the ones that will be going into the model. Next, we're going to do assumption checking. So we have a continuous variable, which is total self-esteem, and we have our categorical variable, which is sex. So normal distribution, first thing I can look at is a histogram. And again, all I did was go back into my Lab 2 information and scroll around until I got to all of those graphs that I was making. The histogram, which is right where we were talking about univariate normality. So I could take just all of this, copy it into my lab that I'm currently on, or whatever script I'm currently working on, and then just adjust the things that need to be adjusted, like what item in the environment am I targeting, what variable am I targeting, and change the labels so that they match what I want to do. Running that, we have a nice little histogram here, which does not look normally distributed at all. Very strong negative skew going on here. So not going to report that as even looking anywhere near normal. But let's go ahead and get the Shapiro's test as well. And Shapiro's test has a p-value of 0.14 zeros and then 5992. That's very much less than p05. So doesn't seem like this is normally distributed. I would say it's got a violation of normality. But let's go ahead and look at the normality according to gender. Like, we can get some detailed descriptives by using the psych package, like if we want to get skew and kurtosis. Load up psych and then do a describe by function. Describe self-esteem grouped by sex. So if I run that, I have some information down here, very similar to using the Explorer in SPSS. So I have the mean and standard deviation, I have the median, I have the trimmed mean, I have min and max, I have skew at negative 0.75, and I have kurtosis at negative 0.43. Same thing with the female. So notice this is different by male and female, and it would match the mean and standard deviations you have here in your Descript2 table that we asked for before. It's just easier to see this little table that we made before than trying to find them in here. What this extra information gives us is some information about the skewness and kurtosis. But we can also get a histogram that is showing us both the male and female types within the histogram. And what I did here, I went ahead and looked at AI to see if it could help me with that. First, I told it what I was doing, like the first one. Like I just copied my own code into here, right? And then ChatGPT says, looks like this is what you're doing. Well, that's good. It shows me that we're both on the same page. And then I said, can I have two overlaid histograms, one for male and one for female, in the category in the histogram? And it said sure, and it gave me how to do that. Said that I had to add these pieces, like position identity. And when it did that one, it was okay. It was like really right on top, like the male column was on top of the female column, so it didn't quite look like what I was after, but it did work. And then I said, well, I want to put the histogram bars for male and female beside each other instead of overlaid. I mean, I asked it for overlaid, and that's what it gave me. But I realized that wasn't really what I was after. So can we put the male and female beside each other instead of on top? And it said, yeah, instead of the identity, we're going to use Dodge. So that's what I ended up with in our script. I did position Dodge so that they would be beside each other. And I thought the blue and pink is what ChatGPT came up with. So it's very gender normed, I guess. And I was like, okay, that's fine. So running that one, I thought, okay, that's a cute graph. I can work with that. That would make a pretty little graphic for my write-up. So, and then of course, that's our visual inspection of the histogram by male and female for total self-esteem. But I also want to run Shapiro-Wilks normality test to see if either of the distributions for male or female are going to make the Shapiro-Wilks test. So here we have, I'm just giving it that name, Shapiro results. You can name it whatever you want. Assigned by Lab 7.1, then group by sex, then summarize the p-value of the Shapiro test. And that way I'm able to see just the p-value. I don't really need the actual estimate of Shapiro-Wilks test because as a assumption check, I'm interested in was it significant or not, right? So that's all I need out of there. Running that, and now since it's in the environment, I can print it. And print just puts it into our console down here. So the p-value for Shapiro-Wilks test for the males was significant at lots of 9 zeros before we get to 892, and the Shapiro-Wilks test was significant for females, which was 11 zeros before we get to 511. So back to our scientific notation, if you see a negative, E negative number, it means it's very, very small. That's how many zeros would go after the decimal point before those numbers. But if you saw a positive, it would mean adding more zeros, a very large number. Okay, so that's our univariate normality and for total self-esteem. So we're going to conclude that with a significant Shapiro-Wilks and those histograms, that there is a violation of normal distribution. So we'd want to let our reader know that. With a t-test, especially independent t-test here, we want to check the homogeneity of variance for the outcome between those two groups. And for that, we're going to use Levine's test. We can find a good Levine's test in the package called CAR. So install and load CAR. And then the function is called Levine's test. Then we put the outcome, total self-esteem, predicted by the categorical variable. And what data set are we referring to? So we'll run that. And looks like our Levine's test comes in at a significance level of 0.1126, which is not less than 0.05. So it's not significant. We conclude there's no violation of homogeneity of variance. So now that we have our preliminary checks done, we've checked our assumptions, we've grabbed some descriptives, we're ready to do some model testing for that independent t-test. We're finally ready for model testing. So here's the line that we run for conducting a independent samples t-test. It says create a new object. We're going to call it IND_t-test. It's going to be assigned by using the function t-test, t.test. We're predicting total self-esteem by the sex variable using dataset Lab 7.1. And then this var equals true. We're putting that statement because we had a non-significant Levine's test. So we are assuming equal variation between males and females in terms of the variation of total self-esteem. If we had had a significant Levine's test, we would change this to false. And what happens when you put a false there, it runs a different type of correction onto the t-test estimation. It's called a Welch's correction. We need to run this, and then to see the results, we have to print it into the console. So let's see what we got here. We have the two-sample t-test, and there's our t-estimate. our degrees of freedom, and the significance value. Now, it looks like our t-test is non-significant. In other words, there is no real difference, no significant difference between average total self-esteem between males and females. So the alternative hypothesis, if it was significant, would say that there is a difference. But because we have no significant t-test or a non-significant t-test, we conclude there is no true or significant difference between these groups. So, what else do we need here to be able to write this up? We have the t-estimate, we have degrees of freedom, and we have the significance value. We still need the effect size. And effect size type for a t-test is typically Cohen's d. So we could get the formula for calculating Cohen's d and use R like a big old calculator and put in the formula for R to calculate from, but I'd rather just get a new package. So we're going to use the package called LSR, and loading that, they have a function called Cohen's d, and then it's just that same formula of total self-esteem predicted by sex using the dataset 7.1. And we see down here in our console that Cohen's d came in at 0.16. So we interpret Cohen's d using some cutoffs. I put them in our write-up. Cohen's d, a 0.2 is small, a 0.5 is medium, and a 0.8 is large. And we have a 0.16, which is less than small, very little. So a very unimpressive effect size with this non-significant test. That makes sense. And while we have a nice histogram, a box plot would be useful here for helping communicate information about it. And again, I went back to our Lab 2, and I also grabbed some of this blue and pink stuff from what ChatGPT gave me before, and I adjusted what data and what variables are being used and came up with this. You can also play around with it. Play around with what you would like it to do. When you see a graph, say, what do I like, what do I don't like? See if you can figure out differences you can do in the code to make it what you want it to be for the write-up. When I run this, I get a cute little box plot with its labels and flipped. So pretty cool. And I can use that in my write-up. In fact, let's go check out the write-up. This one is for independent samples t-test. So as usual, we let the reader know what type of test was conducted, what were we about, what variables were in it. We have the mean and standard deviation of total self-esteem for the males and the females. Told the reader about the visual inspection of the total self-esteem across both genders and the significant Shapiro's Wilks test. And then the information about the test. The difference was not significant, and there's my stats line. And I can let the reader know if there's a figure involved. My little interpretation statement in the end. In other words, there were no significant nor practical differences in self-esteem between males and females. So the box plot I got out of SPSS looked like this. And if I wanted to put in this box plot, I could just export to image and be able to put that one in my write-up. So good there for our independent t-test. moving into our part 2, our paired samples t-test, is looking at a different question here. We're looking at, is there a significant change in participants' scores on their fear of statistics following a intervention? So you might do an intervention at a workplace or an intervention with a client where you take their score at the beginning, the pretest, you do the intervention, and then you do their score. You test them the same test again to see if there's been a significant difference between time 1 and time 2. With those 2 time points on the same person, you're talking a paired samples t-test. So again, we're going to import the data set, the SPSS data set, and this one's called experim.sav. It's also with your Pallant SPSS Survival guidebook. So have that in your working directory, and then you're able to import it into your environment. And we should have 30 observations of 18 variables. Let's look at what we have in here in the console. So we have ID, looks like it's being treated as a number. We have sex being treated as a number. And group definitely looks like that needs to be categorical because a min from 1 to a max of 2 kind of says that's going to be a categorical. All these others seem to be continuous except for these last 3, depression, time 1, time 2, time 3. So not going to worry about those, but it looks like we need to do some cleaning up in this area so that we can pull descriptives on it. It's kind of hard to pull descriptives on a category that's not being recognized as a category. So let's look at that. Same thing we did before. To set the ID as a character, we just let R know to recode the ID variable to a character and then write it on top of the ID variable already there. So that's not going to add an extra variable. But then these, where I'm saying take the sex variable and now write it onto a variable called sex.f, that's 2 different things to R. But I'm converting the sex variable to a factor and giving it the labels, just like we did in Lab 2 and earlier in this lab. And then the group is actually 2 different classes or 2 different interventions that the participants were involved in. They were either assigned to a math skills intervention or a confidence building intervention. And that was to help them get over this fear of statistics, right? So, and how did I know that? I looked at the code book. So running those, and now let's take a look at the data set, specifically those items. We have sex, we have 15 male and 15 female. So very controlled situation, right? Very independent variable controlled. I have 15 male, 15 female. We've assigned 15 to the math skills intervention and 15 to the confidence building intervention. And our ID variable is now a character. Now, with that like even split between males and females and which group they were in, it makes me wonder, because they're not even, 15 is not an even number, how did they distribute to those 2 interventions? And we can do that by using that table function that's in the janitor package that we already loaded up. And I'm going to call it, whatever you want to call it is fine. I'm going to call it gender by group as an item in my environment using a table or tabling from the Lab 7.3 data. And the 2 things I want tabled are sex by group. So I will put that in and then hit print. And print puts it down here in the console. I can see that 8 males were put into the math skills and 7 males were put into the confidence building intervention, and then vice versa for the female. It'll probably give us a nice little table here. Yep, that's pretty. Okay, so a lot of prep, just getting things in there, getting an idea of what these variables are, and now we're ready to start our preliminary work, getting this stuff ready to analyze. We can make a smaller data set more manageable, because really, when it comes down to it, for the paired t-test, we're only really concerned with the scores of fear of statistics at time 1 and the scores of fear of statistics at time 2. That's all we're really interested in here. So I'm going to create Lab 7.4, selecting only those 2 variables. And we have 30 observations of 2 variables. We still need descriptives for these, and we can get that by, similar to what we did before, assigning a new thing in the environment. I'll call it descript 4. It's from the data Lab 7.4. Then summarize the following things. The mean of FOST1, call it mean FOST1. The standard deviation of FOST1, call it SD FOST1. The mean of FOST2, call it mean underscore FOST2. And the standard deviation of FOST2, we're going to call it SD FOST2. And I can take a good little look at that up here and be able to use that for my write-up information. Okay, I still need to check normality, but for our paired samples t-test, I'm checking the normality of the difference between FOST1 and FOST2. So I need to compute a new variable. And similar to that we've done in a prior lab, where we're going to create a new thing assigned by this formula. So I'm just saying this score minus this score is now going to become this new variable in this data set. So now I have 30 observations of 3 variables. And now that it is a variable, a continuous variable, I can go ahead and check the histogram for it and run normality tests on it. Same as I did before with getting my histogram and maybe giving it some labels, making it more interesting to look at and more approachable in case I want to use this in my write-up. So here's my histogram of the difference scores. It looks pretty choppy to me. I mean, it's rounded if you ignore these low bins. We can do bin width, maybe 0.5. Let's see if that'll work. A little different. So play around with the code, see what looks good to you in terms of helping your reader understand what you're conveying. And of course, we can run Shapiro's test on that continuous variable that we just made. Looks like just barely squeaked by on significance. So we have a non-significant Shapiro-Wilks, but very close. It is greater than 0.05. So you can let your reader know what you think of the distribution and that the Shapiro-Wilks test came in non-significant. Okay, speaking of graphs, a nice bar chart would do good here. But it takes some doing because of the values being 2 continuous values that we want to put into one figure, having both of those bar charts of 2 different variables. So it can take a little doing. I fished around a good bit before I found something I liked, and you see what you can find as well. What I came up with is, first I had to combine the means of the FOST1, FOST2 variables into a baby table and save that into the environment. So I called this new item, this new object in the environment, mean values. It's assigned by the combination of the mean for FOST1 and the mean of FOST2. Okay, running that. Now in my values area, I have mean values. Now I want to combine the values into a data frame object so that with the mean values and the variable names. So I'm going to make this data frame. I'm going to call it mean underscore data frame, and it's going to be assigned by the function turn this into a data frame, the variables of time 1 and time 2, and mean value equaling the mean values, which I already have over here, right? So we already have the mean values. There's going to be a variable mean value. So running this, and now I have that mean data frame. If I look at it, it looks like that. Pretty little, pretty just basic, right? Now I'm ready to do that bar chart. And I'm going to use that data frame object I just built. Give me a ggplot using the mean data frame that we just made. The aesthetics are x is variable and y is mean value. And then put the fill using whatever the value from the variable. I'm doing geobar identity and putting them beside each other. I'm giving labels. I'm giving a title. Theme minimal is to keep it from being too like with the grid lines and all of that. And then when I was running and playing with it, I found that I didn't want the legend there because it was kind of obvious what time 1 and time 2 were with the title and everything. So I plugged it into ChatGPT and I said, how can I do this without the legend? And it said to add this piece on it. So here's what we came up with. Little bar chart, time 1 and time 2 with my labels, no legend. So that's something that I feel like, okay, I can use that in a write-up. That looks pretty cool. So then, distracted by the pretty pictures, I know. It's a final thing we need to do to be ready to run this analysis is we have to get the data ready for a paired t-test. And one thing that we haven't really discussed before is the difference between long data and wide data. And to run a paired t-test in R, we need the data to be long instead of wide. And I'll show you what I mean by that. I'm going to go over to the write-up that is the SPSS write-up, or the lab. And on the last page, I created this little example of what's going on between wide data and long data. So wide data is what the data set currently is like. It's arranged by person, right? For person 11, they had these time 1 scores, these time 2 scores, these time 3 scores. And so the data set gets really wide because it's by person who's being measured multiple times. What R needs the data to be in is long, so it needs to be arranged by occurrence, not by person. So we need occurrence 1, occurrence 2, occurrence 3, occurrence 1, occurrence 2, occurrence 3. It needs to be on separate lines, separate observations there. So long data would look like this, where I have the person's ID, some things don't change. They were always that sex, that age, in that group. But then they have their time 1 scores for these 3 items, and there are time 2 scores for these 3 items, time 3 scores for these 3 items, and then you go to the next ID person, the next person. So the color coding is to show you how it translates from wide to long. And we don't do this by hand, but we do have to do some coding to get R to do this. You can also do wide to long data and do that pivoting in SPSS, but you don't have to for the paired t-test, so we don't do it. We do have to do it in R. So I'll show you how that's done. What we're going to do here, converting the long format, this says create a new object in the environment called long data. Use Datasets 7.4, and I want to restructure by pivoting. I want to pivot the information and specifically take the variables that begin with the word FOST and put them into a variable called time. So then the values in that time variable would be FOST1, FOST2, FOST1, FOST2, FOST1, FOST2, and so on. And then take the values of FOST and put them into a variable called score. So whatever value it had, it's now going to be pivoted over and put into a variable named score in this turned table. So let's run that and we'll take a look at what this looks like one step at a time. See what I mean? And we can ignore the difference one that we made. We can see that the difference between 50 and 48 is 2. The difference between 47 and 45 is 2. But this is what we were really working on, the time variable and the score. So with all of that, now we're going to convert the time variable to numeric, because right now it's a string. It says FOST1 and FOST2. But what we're going to do here is use the function gsub to globally substitute the information in the time variable. What are we going to substitute it with? We're going to replace every FOST with a blank. That right there, just quotation with nothing between it. It's being replaced with nothing. So it's pretty much erasing the word FOST, which leaves only that numeral. So FOST1 will now be just 1, and FOST2 will now be just 2. Now that we have that substitution done, we're going to convert that leftover numeral to a numeric measurement type, 1, 2, 1, 2, right? And we're going to apply these changes back to the time variable in the long data frame. So let's run that, and then we'll take another look. So now we got 1, 2, 1, 2, 1, 2, 1, 2, instead of the FOST1, FOST2. That's the tasks we needed to do to get this data ready for a paired samples t-test. We're finally ready for that test. So similar to what we did before in the independent t-test, we're going to assign an object in the environment, and we're going to call it DEP_t-test, assigned by the function of t.test onto score predicted by time. In other words, is there a difference in score based on the time 1 measurement or the time 2 measurement? The data being used are the long data that we put in there, and here we got to let R know that this is a paired samples test. So running this, we can check our console for the results with print DEP t-test. So we have our t-test value, we have our degrees of freedom, and our p-value. And the p-value is significant, lots of zeros. So we have a significant difference between what? Between time 1 scores and time 2 scores. So what else do we need here to be able to report this? We need coincidence effect size. And yes, a new package. Why not? This one's called RStatics. So we'll load that. And this one uses coincidence saying using long data, score predicted by time, paired true. So we have our effect size of 985, and at least in R, it even tells you what the magnitude is, that it's a large magnitude, which we can also see on our cutoffs table for coincidence. So, wow, right? A lot of skills. We definitely pushed into more R maneuvering and data cleaning and making new variables, and it's stuff we've done before, a lot of it, but now actually applying it in a new situation. So you want to keep doing that and looking for ways to get to the coding you want to do what you want. So let's go back to the write-up and see this second one right here. A paired samples t-test was conducted to evaluate the differences of 30 students' fear of statistics scores before the intervention, and then you're able to tell your reader what was the score at the beginning, and after the intervention. You can let your reader know if there's a figure involved to help them visualize what's going on. The difference between time 1 and time scores was evaluated by normal distribution. So that's my assumption check of the difference score, saying is the difference normally distributed. And I don't know, I thought the histogram looked a little choppy, and I thought it looked kind of positive skewed. However, the Shapiro-Wilks test was non-significant, which indicated normality assumption has been met. So you just let your reader know what you found. It's fine if you think that's normal, say it's normal. If you think it's looking kind of skewy kurtotically, then say that. But then just tell your reader what the Shapiro-Wilks came in as well. Then your results for your test was a significant decrease in the fear of statistics test scores. There's my T line, my stats line. Due to the large effect size, results showed a significant practical impact to the intervention on students' attitudes regarding statistics. So my interpretation statement, what does this mean? How is it even relevant, right? So that's kind of just the model testing part. I worked in the assumptions check into this, but you would have a paragraph in your homework. You would have a paragraph ahead giving your reader some context of the data set or any other sample description that helps you communicate about that data. Okay, so got a lot done here. We did 2 types of t-tests, an independent samples and a paired samples. We definitely checked a lot of different assumptions specific to t-tests and got a lot more actually doing the coding that we've already started before, but now adding to it and adding new coding in. So good job, really learned a lot on this one, and looking forward to seeing you at the next lab.